Ever wonder where nuclear energy comes from? The answer lies within a unique metal, uranium. This powerhouse of an element is more than just a heavy metal. It's a key player in the world of nuclear energy. Uranium was first discovered in the late 18th century by a German chemist named Martin Heinrich Klaproth. He named it after the planet Uranus, a fitting name for an element with such out-of-this-world capabilities. But it wasn't until the 20th century that scientists truly began to understand the power locked within this dense gray metal. The heart of uranium's energy-producing power lies in its nucleus. When struck by a neutron, this nucleus can split in a process known as nuclear fission. This splitting releases a tremendous amount of energy, along with additional neutrons that can go on to split more uranium nuclei. This chain reaction is the process that fuels nuclear power plants, providing electricity for millions of homes and businesses around the globe. But uranium isn't just used for power generation. It's also a key component in the creation of nuclear weapons, a testament to its incredible and potentially destructive power. This dual nature is a reminder of the responsibility we carry in harnessing the capabilities of such potent elements. Uranium's unique properties also make it useful in other areas. Its density, for example, makes it ideal for use in tank armor and the keels of yachts. It's also used in the production of certain types of glass and ceramics, adding a distinctive yellow or green color. Uranium truly is an extraordinary element. It's a testament to the power hidden within the atomic structure of the world around us, a power that can be harnessed to light up cities or level them. It's a reminder of the incredible potential and potential danger that lies within the elements of our world. And so, we uncover the story of uranium, an element that holds within its nucleus the power of the stars. Uranium, an extraordinary element that powers our world and propels us into the future. Now, imagine metals so reactive they explode on contact with water. Meet cesium and rubidium. These two elements, found in the same group of the periodic table, are infamous for their explosive personalities. Cesium, the first of the duo, is a soft and silvery gold metal. It's one of only 5 elemental metals that are liquid at or near room temperature. But don't let its delicate appearance fool you. When cesium encounters water, it reacts violently, creating an explosion and releasing hydrogen gas. Rubidium, on the other hand, is a soft, silvery white metal. Like its sibling cesium, it too has a fiery temper. It reacts rapidly with oxygen in the air and violently with water, producing flames of a beautiful purple color. Now you may wonder, who would dare to discover such volatile elements? The credit goes to Robert Bunsen and Gustav Kirchhoff. These 19th century chemists discovered both cesium and rubidium using a tool called the spectroscope, which separates light into a spectrum. Cesium, named after the Latin word cesius for sky blue, was identified by its bright blue spectral lines. Rubidium, named after the Latin word rubidus for deepest red, was recognized by its deep red spectral lines. Even though these metals can be dangerous, they also have their uses. Cesium is utilized in atomic clocks, which are the most accurate timekeeping devices in the world. Rubidium, despite its reactivity, finds use in fireworks to give them a lovely purple hue. It's fascinating how two such volatile elements can be so useful. But remember, they are not toys. They must be handled with extreme care, under controlled conditions, and always with adequate safety measures. Cesium and rubidium, volatile yet fascinating, adding a bang to our exploration of metals. But how do we transform uranium's potential into usable energy? That's the question that led to the development of nuclear power, a testament to human ingenuity and the power of uranium. It all starts with a process known as nuclear fission. When a neutron collides with a uranium atom, the atom splits, releasing a large amount of energy in the form of heat. This heat is then used to produce steam, which powers turbines to generate electricity. The splitting of the atom also releases additional neutrons, which can then collide with other uranium atoms, creating a chain reaction that keeps the process going. The heart of this process is the nuclear reactor. Inside the reactor, uranium fuel rods are submerged in water. As the uranium undergoes fission, the heat generated turns the water into steam. The steam then drives turbines, and the turbines generate electricity. But why use uranium? Well, uranium is incredibly energy dense. A single pellet of uranium fuel, about the size of a fingertip, can produce as much energy as a ton of coal or 3 barrels of oil. And while uranium is a finite resource, it's also incredibly abundant. There's enough uranium in the Earth's crust to power our current energy needs for hundreds of thousands of years. The benefits of nuclear power are numerous. It's a low-carbon source of energy, producing virtually no greenhouse gases. It's also a reliable source of power, capable of generating electricity around the clock, regardless of the weather. And it's efficient, with modern reactors able to use over 90% of the energy in their fuel. Of course, nuclear power isn't without its challenges. The process produces radioactive waste, which must be carefully managed and disposed of. And there are safety concerns, from the risk of accidents to the potential misuse of nuclear materials. But with careful regulation and technological advancements, these challenges can be managed. Nuclear power, a testament to human ingenuity and the power of uranium. It's a prime example of how we can harness the extraordinary properties of the elements around us for the benefit of humanity. Explosive reactions can be more than just dramatic displays. They have practical applications too. Our explosive friends, cesium and rubidium, may be known for their spectacular reactions with water, but their explosive nature is put to good use in various industries. Let's start with cesium. This silvery gold soft metal is not just a pyrotechnic spectacle. It has found a home in the world of medicine and healthcare. Cesium is used in cancer treatment, specifically for a procedure called brachytherapy. In this treatment, cesium is placed in or near the cancerous tissue, delivering a high dose of radiation to destroy the harmful cells while sparing the healthy tissue around it. Now, let's turn our attention to rubidium. This soft, silvery white metal is not just an explosive wonder,